Good morning, everyone. Not quite 9:30 yet, so we'll wait just a minute till we hit 9:30 and then we'll start talking. Okay. All right, it's 9:30, so let's go ahead and get started. So we are finally coming up on the end of the semester. We have two chapters left, chapter 7 and chapter 8. Chapter 7 is probably the longest chapter all semester long. In fact, you'll notice that for the quizzes, there's a 7A and a 7B. That's because there is so much material in chapter 7. We're going to take our time with it. We have lots of time left this semester, so we're not going to rush through the whole chapter, right? We're going to take our time getting through the material. But I will say that one of the reasons students often struggle with this chapter is because it relies heavily on material that you learned previously. If there are certain things that you struggled with or didn't do well with, those are the things that you're going to have a hard time with this semester. As I said, you can't just memorize a few facts in chemistry and then spit those same facts back out on a test and expect to do well. Chemistry, much like physics, is a science of application. You have to apply the things you learned. And so this chapter, we're going to cover how to write a chemical equation, how to balance that chemical equation, how to identify what sorts of new molecules you can make in a chemical equation. Then we're going to discuss how much you can get, so if you have 5 grams of this compound and 5 grams of this compound, how much product can you make? We're also going to talk about things like oxidation and reduction, which relies heavily on understanding electrons and electron configuration. There's a lot of dimensional analysis in this chapter from chapter 1. There's a lot of nomenclature in this chapter. So understanding how to get the formula of a compound from the name of a compound. So there's a lot of material in this chapter that comes or builds upon materials from previous chapters. If you are struggling or stressing over a certain section, I really recommend that you take this week and this weekend to go back over those materials. Again, we're going to take our time going through this chapter. We're not going to race through it. We've got lots of time to get through it. But it definitely requires you to have knowledge from most of the chapters that we've previously covered. And so please take some time this week, take some time this weekend to look over some of those things that maybe you're not as strong on, because you're going to need that knowledge to get through this chapter. Also, believe it or not, the final exam is coming up, right? Probably faster than most of you want. If you don't have an A in the class, you have to take the final exam. If you have an A, you're exempt. So you don't want to wait until we end all of the material to start studying for the final. That's a bad plan. I know most of you on here I can see are doing pretty well and are keeping up with the material, but some of you, and especially for those of you who are watching this recorded version at a later time, every single lecture I mentioned, do not wait until the last minute to try those quizzes. And every single lecture or course period unit, whatever, you guys wait until the last minute, you don't take the quizzes, you either end up with a 0 or a poor grade on the quizzes. And then it in turn affects your test grade, right? Some of you did not do so hot on the test. And I could tell that you waited till the last second to finish the chapter 6 homework. You waited till the last second to practice the quizzes and you didn't do well. Well, maybe how about, for this last unit and these last 2 chapters, maybe you listen to me for once and you don't wait until the last second to do the quizzes, particularly because this time there's 3 of them. There's 7A, 7B, and chapter 8. Okay, we have a tough schedule coming up, right? Think about it like football. This is the final push towards the playoffs, guys. Put your best effort forward. So let's take a look real quick at what's coming up due. Okay. So the reading, as I said, I made a mistake on the due date of the reading. I am not going to change it. I'm going to leave that as is. I strongly suggest you do the reading sooner rather than later, but I'm not going to change it. Okay, that date is in there. I'm not going to mess with it. You will have a course ticket due on Wednesday, right? You're going to have a course ticket based on today's material due on Wednesday. Okay, you will have a lab due on Thursday. Okay, a lab due on Thursday. Although depending on how far we get, you guys might want to ask your lab instructor for an extension on this guy, because I don't know that we're necessarily going to get to this particular material. You can tell him I said, you know, we're not quite at that material yet. And if he reaches out to me, I'll let him know the same thing. But you do have a lab due on Thursday. And you will have, of course, after Wednesday's lecture, another course ticket due, and your first homework assignment for this chapter due on Sunday. So you've got quite a bit coming up. It's best that you keep up with it, right? Don't let it all build up till the last minute. Okay, so let's start talking about chapter 7. Chapter 7 is all about chemical reactions. Chemical reactions, counting atoms, balancing chemical equations. Then when we get further into it, we're going to talk about types of reactions, identifying what kind of a reaction you have going on. We're going to talk about you guys writing a chemical reaction, so identifying what sorts of things you can make, right? And then writing those correct chemical equations. And then in a couple weeks, right, again, we're going to get into talking about something called stoichiometry, which is how much can I make? Okay, we're going to talk about things like limiting reactants, what prevents us from making more in our chemical equation. We're going to talk about things like theoretical yields, right, versus actual yields. So how much can I make based on what the math tells me versus how much can I make based on my actual results in a lab? Okay. And then finally, we're going to talk about oxidation reduction reactions, right, which is really important in Chem 2. So we've got a lot of things to talk about. All right, so let's start with chemical reactions. Okay. Oh, this is what I just said. We're going to talk about describing a chemical reaction. We're going to balance it. We're going to classify it, and then we're going to write our own. Okay, so what is a chemical reaction? Okay, it's a process where one or more elements or compounds, so atoms or molecules, are changed into one or more different substances. Okay, so it's a process where the original substance, your starting stuff, changes into a new substance with completely different properties. And we've talked about some of the properties of atoms and molecules in the previous chapter when we talked about intermolecular forces. We talked about vapor pressure, we talked about boiling points and melting points. So we're looking at creating new substances with new properties, different vapor pressures, different intermolecular forces, different melting points, different boiling points, different chemical properties. Okay. So the question is are new atoms created? Okay, are other atoms destroyed? So we're changing, right, from one substance into another, but are we creating new atoms and are we destroying other atoms? Well, the answer to that is no. Matter is never created or destroyed. Instead, what we're doing is we're rearranging, okay? So the mass and types of atoms that make up our reactants must be equal to the mass and types of atoms in the products. Instead of creating new atoms, we're rearranging them. So think back to the chapter where we talked about Lewis structures and Vesper theory, and we talked about, you know, how we had molecules, right, which were connected to atoms connected to each other by bonds. Okay, you cannot destroy an atom or create a new atom. What you can do, though, is you can rearrange them. So you can take this atom, right, and connect it to a new atom. So you can rearrange them and make new connections between different atoms. What you cannot do is create gold from any other element, right? So you can't take silver and turn it into gold because those are atoms, right? You have atoms of silver on the periodic table. Right, remember our handy dandy periodic table here? We've got silver, we've got gold. Right? You cannot take silver and turn it into gold. You cannot take one element and turn it into another. However, if you have gold atoms, you can rearrange them. You can take them off of, break the connection between one atom, right, and put it onto another atom. So this is really important whenever you're dealing with chemical equations of any kind. You need to remember that the mass, right, the mass and types of atoms that make up the reactants must be equal on both sides. Okay, so reactants and products. Reactants are the original substances. So you're going to hear me say reactants and products a lot this chapter. Reactants are your starting stuff. It's your original substance. It's the thing that you made, or the thing that you started with, rather. Products are the new substances. These are the things that you made. Okay, so product is what you get when you rearrange the atoms in your original substance, your reactant. Okay, so product is what you made. Think of it like product, right? When you talk about in the business world, your product is the thing you make. Reactant is the thing that you started with. It's the thing you react together to get something new. Okay, so in this chemical equation, the reactants are the HCl, hydrochloric acid, and zinc metal. Reactants are always on the left side of the equation. So these are my two starting products. I have hydrochloric acid and solid zinc metal. Those are my reactants, my starting things. Products, or the new thing that I made, are found on the right-hand side of the arrow. So on the right, here's my arrow. On the right-hand side, I have zinc 2 chloride and hydrogen gas. Okay, so again, reactants are always on the left-hand side of my chemical equation. Products are always found on the right-hand side of my chemical equation. So whenever you're looking at a chemical equation, you can quickly and easily identify the reactants by looking at the left side of the arrow and the products by looking at the right-hand side of the arrow. Okay. The arrow in the equation is what indicates to us, or it means yields or produces. So we can read our chemical equation like a sentence. And this sentence says 2 hydrochloric acid in the aqueous state plus solid zinc yield or produce zinc 2 chloride in the aqueous state and hydrogen gas. Okay, so that's what my chemical equation is telling me. The arrow means yields or produces. These little letters down here in parentheses indicate the state of matter. So S indicates solid, G indicates gas. What do you guys think an L would indicate?
Liquid.
Liquid, yep. So solid, gas, liquid. And AQ, right? Whenever you see a little AQ, that stands for aqueous, which means you're dealing with a solution. Remember that a solution is usually some sort of solid or liquid dissolved into another liquid, right? So oftentimes in chemistry, we deal with a lot of things that are dissolved in water, and aqueous indicates that you're dealing with a solution whose solvent is water. Okay, remember the solvent is the thing present in the larger amount. So whenever you see a little AQ, that indicates that you're dealing with a solution, right, which is something mixed with something else. And specifically, it indicates that the solvent, the thing it's mixed with, is water. So we have hydrochloric acid dissolved in water. Okay. Okay. So again, you can read this like a sentence. 2 hydrochloric acid dissolved in water plus solid zinc metal yields or produces zinc 2 chloride dissolved in water and hydrogen gas. Okay, so how do you know if a chemical reaction is taking place? This is particularly important in the lab. So when you're in the lab and you mix two things together, especially if they're both clear things, how do you know that a chemical reaction has occurred? Well, there's a couple of clues. First is that the temperature changes without you heating or cooling it. So if you mix two things together and you're holding the beaker in your hand and the beaker suddenly gets cold or suddenly gets hot without you adding any heat or cooling it down on your own, then you know a chemical reaction has occurred. Okay. If it bubbles, right, that means that a gas was produced, which is usually evidence of a chemical reaction. If a precipitate forms, and we're going to see a lot about precipitation reactions. A precipitate just means a solid. So if you take two liquids and you pour them into the same beaker, right? And all of a sudden you get a solid at the bottom of your beaker, that is an excellent indication that you had a chemical reaction taking place. And in fact, when we start talking about the classifications of chemical reactions, precipitation reactions are a big one. That's where you mix two liquids together and a solid called the precipitate forms. Okay. And then finally, the third one is a permanent change in color. That's also a good indication that you have a chemical reaction. Okay, but be careful because sometimes a physical change can produce some of those observations. For example, if you dump food coloring in water, you're going to change the color of the water, but that's not a chemical reaction, right? The dye in the food coloring is not reacting with the water and creating something new. Okay. If you boil water, you're putting heat in there, which is causing the water to change phase, right? You're causing the water to go from a liquid to a gas, but that is not a chemical reaction. That's a physical change. You're changing the state from liquid to gas. You are not adding new atoms, right? A new substance and rearranging the atoms of the water molecule with that new substance. So just because something is bubbling doesn't necessarily mean there's a chemical reaction, particularly if you're heating it up, right? If you're heating it up, you're putting heat in, right? There's a good chance that it's bubbling because it's boiling and you are changing phase, not creating a new chemical reaction. So again, just be a little careful because not just because something changes color doesn't always mean a chemical reaction. Okay, so if we were to add hydrochloric acid to zinc metal, we would produce bubbling and a temperature increase. And I think, oh no, you guys are my online class, so you're not in the lab at all. You won't get to do this. But we do this in the face-to-face version of 1211. We actually have strips of zinc metal and you guys put it in hydrochloric acid so you can actually see what's going on. When you do this, when you take zinc metal and drop it in an acid, right, immediately what you see is the test tube starts to bubble, right, and the test tube gets hot. Okay, and those are our two indications that we have a chemical reaction occurring because you don't have to put a flame under the test tube for the bubbling to occur, right? The second you drop that metal in, the bubbling starts, right? That's not boiling. That is an actual reaction between the zinc metal and the hydrochloric acid, and the beaker gets hot without you putting, again, any heat into it. And again, that's because this reaction, part of its products are heat. Okay. So again, keep in mind that we're talking about atoms and molecules being rearranged during the reaction. So what does this look like? Okay, so this is what it looks like. And this is the same reaction we just saw a minute ago, right? Hydrochloric acid in water, aqueous, mixed with solid zinc metal gives us hydrogen gas, which is the bubbling, right? Remember I said it bubbles? Okay, the reason it bubbles is because you're mixing together a liquid solution, right? Aqueous, right? Hydrochloric acid dissolved in water and a solid, right? And you're getting a gas. So you're mixing two substances in the liquid state and you're getting a gas. And that's what causes the bubbles. Okay, and then zinc 2 chloride is your other product. Okay, this type of reaction is called a single replacement reaction. And the reason it's called a single replacement reaction is because one single thing is replacing something else. So in this case, we have a hydrogen bonded to a chlorine and a zinc atom by itself. After my reaction, the zinc has replaced the hydrogen. So I get now zinc chloride instead of hydrogen chloride. So my zinc has replaced the hydrogen. Okay, so again, we're talking about a rearrangement of bonds. So initially we had a zinc atom off by itself, right? And then we had a chlorine atom, okay, that was bonded. Take one out here. Okay, we had a chlorine bonded to a hydrogen. Okay, so chlorine bonded to a hydrogen, zinc off by itself. What happened was the zinc came along and replaced the hydrogen. So now the zinc and the chlorine are bonded together. So this is called a single replacement reaction. Okay. We're going to talk in a little while about something called redox reactions, which is short for oxidation reduction reaction. So single replacement reactions also belong to a subcategory of reactions known as redox reactions. Okay. When we start talking about redox reactions, that's where you're going to have to understand the valence electrons, right, that we talked about in the previous chapter, because this depends heavily upon valence electrons. Okay. So before you can correctly write and balance an equation, you must be able to correctly count atoms in chemical formulas. So we're going to learn some basics. So we've talked about molecules, right? We've talked about how they bond, right? Their covalent bonds, their ionic bonds, how they kind of come together. But we need to be able to correctly identify the number of atoms within a molecule before we can start talking about balancing equations. Okay. So in addition to reactants and products, we need to understand the numbers in a chemical equation. The term coefficient refers to the whole number in front of a formula that represents the relative number of moles or molecules of a substance. Okay, it represents the relative number of moles or molecules of a substance. That's the whole number in front of the formula. The subscript is a small number to the lower right of an atom that represents the number of atoms of that element in the molecule. Okay, so this one here, this 2 in green, is the coefficient 2. And this coefficient indicates that you have 2 moles of water. Okay, 2 moles of water. It can also be used to indicate 2 molecules of water, depending on how big, right? Whether you are looking down at the atomic level or whether you are scaling up in terms of stoichiometry. Okay, so that 2 indicates the relative amount of water. Okay, either moles or molecules, depending on, right, depending on your scale. The little 2 in blue is a subscript. And this subscript indicates that there are 2 hydrogen atoms in a molecule of water. So again, the little subscripts, those indicate the relative number of atoms within your molecule. The big number outside of the molecule, right, this number here, that is called a coefficient. And that indicates relative amounts of the molecules. So this refers to the amount of molecules. This refers to the number of atoms within your molecule. Okay. So if I ask you, how many atoms are in this formula? How many total atoms are in this formula? What would you guess?
3.
3. Yep, because we have 2 oxygens. This little 2 indicates that you have 2 oxygens. Okay, and there is nothing written here, so we can imagine a little imaginary 1. So you have 2 oxygens and 1 carbon. So that indicates, right, there is an imaginary 1 out here that indicates that you have 1 mole of carbon dioxide or 1 molecule of carbon dioxide. These numbers down here indicate 1 atom of carbon, 2 atoms of oxygen. So a total of 3 atoms in the formula. Okay. How many atoms are in this formula? So how many atoms in 1 molecule of carbon tetrahydride?
15.
Oh, you're close. You're thinking for the whole thing. How many for just the molecule?
Oh, 5.
5.
Yep, 5, right? You have 4 hydrogens, 1 carbon. So 1 atom of carbon, 4 atoms of hydrogen. There are 4 per molecule. And then, yes, you are correct that this 3 indicates that we have 3 of this molecule. So the total number, okay, we have 3 CH4s, so the total atoms would be 15, right? Because you have 3 of these, which means there's 5 atoms in each one of these, so 5, 10, 15. Okay. All right, how many atoms are in this formula?
Seven.
Yep, you're exactly right. 7. Remember, we talked about this when we talked about ionic compounds. The parentheses indicate that you have 3 of the hydroxide group. So you have 3 of that whole thing. Okay. The 3 here indicates that you have 3 of everything inside of the parentheses. So you have 3 oxygens, 3 hydrogens, 1 aluminum. 3 oxygens, 3 hydrogens, 1 aluminum. And that means that there are 3 of these OH bonded to the aluminum. The OH is in parentheses because the oxygen and hydrogen atoms are a pair. Ooh, sorry, my allergies are killing me today. So that means there are 7 atoms in this molecule or formula. Okay. All right. So tell me 2 things. First, how many are in one molecule of this? Then how many total? So tell me first how many are in one molecule of Cr2CO33, and then tell me how many total. So take a second, work that out on your scratch paper. And I have to write it down myself because I don't remember the answer from last semester.
$14.
Yep, that is correct, 14. So in just one molecule of this, you have 2 chromiums, right? That's what this little 2 down here indicates, 2 chromiums. And then remember that this 3 outside of the parentheses indicates that you have 3 carbonate ions, right? You've got 3 carbonates. So 3 carbons and 9 oxygens. Think math. If you're ever stuck about what do you do, remember in math, right? If you have parentheses, you would distribute and you would multiply. 3 times 3 is 9. 3 times 1 is 3. So 9 plus 3 plus 2. It gives you 14 atoms. Now, how many total?
28.
28. Yep. So you have 2 here. So you multiply by the whole thing, you get 28. Okay. So again, CO33 means that there are 3 molecules of this carbonate bonded to 2 chromiums. So you want to be careful when you're counting. There are 14 atoms in the molecule, and we have 2 chromium 3 carbonates, so 28 total atoms. Okay. All right, so now that we know how to count the atoms in a formula, we can start balancing chemical equations. So let's take a look at an already balanced chemical equation. Okay. This is the same chemical equation we've seen a couple times now. This chemical equation indicates that 2 hydrochloric acids dissolved in water, aqueous, plus a solid, 1 solid zinc, right, gives us 1 hydrogen gas and a zinc 2 chloride. Okay. Now, what we want to do is we want to look at, right, this is a balanced chemical equation. So we want to look at what does that mean? The reactants are hydrochloric acid and zinc. The products are hydrogen gas and zinc chloride. Okay. We want to count the atoms in each molecule. Do we have the same on both sides? So HCl, right? HCl, we have 1 hydrogen and 1 chlorine. And then we have 2 of those. So total atoms, we have 4, right? 2 hydrogens, 2 chlorines, plus a zinc, right? And there is an imaginary 1 here. So total atoms on the left-hand side, we have 5 total atoms, right? 2 hydrogens, 2 chlorines, 1 zinc. Okay, now let's look at the right-hand side. We want to ensure that we have 5 atoms on the right-hand side, right? So if you have 5 on the left, you better have 5 on the right. So let's take a look. We have this little subscript 2 down here, which indicates that we have 2 hydrogens. My coefficient is an imaginary 1. So I only have 1 of those. So 2 hydrogens plus 1 zinc plus 2 chlorines. That gives me 5 atoms on the left, 5 atoms on the right. So that's a good start to indicating that our chemical equation is balanced. Okay, we have 5 atoms on the left, 5 atoms on the right. But now the next most important thing, in addition to the number of atoms, we need the same amount of each element on both sides. So for example, like I said, you cannot turn gold into something else. So if I have 1 zinc on the left, I can only have 1 zinc on the right because I can't make more zincs, right? If I've got 1 on the left, I can only have 1 on the right. So let's look and see. In addition to the number of atoms, do we have the same amount of each element on both sides? So let's look at hydrogen, right? And we have hydrogen atoms. They're bonded to a chlorine. I have, according to this coefficient out here, 2 HCl's. So I have essentially 2 hydrogens, each one bonded to a chlorine. So I have 2 hydrogen atoms on the left. On the right-hand side, I have a subscript of 2, which indicates that I have 2 hydrogens bonded to each other. So on the left, I have 2 hydrogens, 1 each bonded to a chlorine. On the right, I have 2 hydrogens bound to each other. So 2 atoms of hydrogen on the left, 2 atoms of hydrogen on the right. So I have the same amount of hydrogen on the left as I have on the right. So far, so good. Okay. Next, let's look at the chlorine. Okay. I have a chlorine bonded to a hydrogen, and then this 2 here indicates that I have 2 of those. So I have 2 chlorines on the left, each one bonded to a hydrogen. So 2 chlorine atoms on the left. Okay. On the right, this little 2 down here indicates to me that I have 2 chlorines both bonded to the same zinc. Okay, so I have, right, essentially here, let me just do a little rearranging here. On the left, I have 2 chlorines. Each one is bonded to a hydrogen. On the right, I have 2 chlorines bonded to a single zinc. So 2 chlorines on the left, 2 chlorines on the right. So far, so good. I have 2 hydrogens on the left, 2 hydrogens on the right, 2 chlorines on the left, 2 chlorines on the right. Now let's look at the zinc. On the left, I have no subscript. So that means that my zinc is not bonded to anything. And I have just an imaginary 1 out here. So I have 1 atom of zinc on the left. It's not bonded to anything, right? It's just hanging out by itself. On the right, this little tiny imaginary 1 down here tells me that I have 1 zinc per zinc chloride. And this imaginary 1 out here tells me that I have 1 zinc chloride. So now I still have 1 zinc atom, but it's bonded to my 2 chlorines. So 1 zinc atom on the left, 1 zinc atom on the right. So I do have the same amount of each element on both sides. So that means that I have a balanced chemical equation because I have equal numbers and kinds of atoms in my reactants as I have in my products. So it's important for both, right? You not only need equal amounts of atoms, but you need equal amounts of each kind on both sides. Okay. So how do we do that? Okay. So again, a well-written chemical equation must represent a real situation, meaning the actual reactants must be able to react and form the products given. It must contain correct formulas for the reactants and products. So for example, remember that certain metals only form one charge. Like lithium, for example, is only a +1 because it's in group 1. So when it is paired with a chlorine, it can only form one lithium to one chlorine, LiCl. You cannot form Li2Cl or Li3Cl. You cannot form LiCl2 or LiCl4. That does not exist, right? That's an ionic compound. Lithium always forms a +1. Chlorine always forms a -1. So when you pair those two things together, they always form LiCl, right? One lithium for one chlorine. So you have to have correct formulas, right? You can't mess with the formula. And then finally, you have to abide by the law of conservation of mass, which means that the atoms cannot be created or destroyed during a chemical reaction. Okay. So again, a well-written chemical equation has to be real, right? It has to have the correct formulas, and you must have the same amounts on both sides. Okay. So how do we balance our chemical equation following those principles? Okay. Well, there's a couple of rules that are going to make your life easier. First, the only numbers you can change in a chemical equation to balance it are the coefficients. Okay. You can only add a coefficient in front of a chemical formula. Okay. This is important. You cannot change any subscripts or add any subscripts. Okay, so you cannot, if you're balancing a chemical equation, you cannot change that O2 to an O3 or an O4 or an O5, right? You cannot change the subscripts or add any subscripts in order to balance your chemical equation. Okay. You cannot place a coefficient in the middle of a chemical formula. So again, you can't stick a 2 here, right? The reason for that is, again, when you have a molecule, that molecule has certain properties. If you change the subscript or the coefficient in the middle of a chemical formula, you have now changed that molecule. So you cannot take a 2 and stick it in the middle, right, in order to make your numbers work out. The only numbers you can change when balancing a chemical equation are the coefficients. Okay, so I know if you're taking notes, write that down right now. The only numbers you can change are the coefficients. You cannot change the subscripts or add any subscripts because otherwise you are changing the meaning of your chemical equation. Okay. And then finally, when you're done, you must end up with the same number and kinds of atoms on both sides of the equation. So no matter what, if you had 2 A's on the left, you better have 2 A's on the right. 4 B's on the left, you better have 4 B's on the right. Okay. So again, the only numbers you can change when balancing a chemical equation are the coefficients. You cannot touch the subscripts or stick a coefficient in the middle of a molecule in order to make what you want. Okay. All right, so let's try to balance an equation. Okay. The word equation says that hydrogen gas plus chlorine gas gives you the molecule hydrogen chloride. Okay. So the first thing we need to be able to do is to take the name of something and identify the formula. Okay, I'm sure you've never heard me say before that that's an important topic, so I'm just going to say it now. Knowing how to get the formula from the name of a compound is really important. Okay, particularly in this chapter. And I know I told you guys there are certain ones you should memorize. I really meant it, because if you have to look it up every single time, right, you're going to have a lot of problems, a lot of stuff to work through. It's going to get tiresome looking up every single time. So there are certain compounds, particularly ionic compounds, that you should be very, very familiar with. Okay, so hydrogen gas plus chlorine gas. Now, hopefully you remember from your reading, right, or your reading assignment somewhere, that there are certain gases that exist in what we call the diatomic state. Okay, that is, let me see here, the common ones that are listed in your textbook are hydrogen gas, oxygen gas, nitrogen gas, chlorine gas, and fluorine gas. Okay, bromine as well. Okay, these guys like to form diatomics. Okay, meaning that in the gas form, right, hydrogen is bonded to itself. So we're going to have H2 plus Cl2, okay, gives hydrogen chloride, okay, in the gas form. It's not an acid in the gas form, right? It's just hydrogen chloride, okay? So again, hydrogen gas plus chlorine gas gives hydrogen chloride gas, okay? But this is not balanced, okay? This is just the formulas written down, but it's not balanced. If we look here, we have two hydrogens, right? Hydrogen bonded to a hydrogen. We have two hydrogens. I'll start my handy little kit here, right? We have two hydrogens bonded to each other. On the right-hand side, we have a hydrogen bonded to a chlorine. So I started with two hydrogens. According to this equation, I ended up with one hydrogen. I can't have that, right? They have to have same numbers on both sides. So when I broke this pair of hydrogens apart, right, and stuck it onto here, I have a hydrogen left over. Well, that hydrogen needs to be bonded to something, right? So I need another chlorine over here. Okay, so I can't go from two hydrogens on the left-hand side to one hydrogen on the right-hand side. Also, on the left-hand side, I had two chlorines bonded to each other, right? So when I broke this guy apart, right, I can't have just one HCl, right? I need two HCls, okay? So unbalanced chemical equation. Let's see how to balance it, okay? Now, we're going to begin by counting atoms on both sides of the arrow. Remember that the number and kinds of atoms in the reactants has to equal the number and kinds of atoms in the products. When I do mine, I always start left to right. So looking at this chemical equation, I have hydrogen and chlorine. So I'm going to start left to right. Okay. So what I'm going to do is I'm going to draw a line, right, to divide the two sides. And then I'm going to list my atoms, right? I have hydrogen and chlorine. I have two hydrogens and two chlorines. Now I want to look at the right-hand side. You should always write the right-hand side in the same order that you wrote the left-hand side, so you can look back and forth across and see if they're the same, okay? So I would always write them in the same order. So writing them in the same order, we can now see that on the left, we have two hydrogens. On the right, we have one. That is not the same, so we're not balanced. On the left, we have two chlorines. On the right, we have one. Again, we're not balanced, right? We do not have the same numbers of hydrogens on both sides. We don't even have the same number of atoms on the both sides, right? We have 2 plus 2 is 4 atoms on the left, and 1 plus 1 is 2 atoms on the right. So we need to balance our equation, okay? So you can see that it appears as if a hydrogen and an oxygen, a hydrogen and a chlorine, were lost in this reaction. So we have to balance. And remember that you can only balance by adding coefficients. We cannot add subscripts. So you cannot come here and just put a little 2 here and a little 2 here, right? The only thing you can change are the coefficients. Okay, so let's put a 2 here in front of the HCl. Now, how does that change the number of hydrogens and the number of chlorines in your molecule? Okay. By putting a 2 here, that now means you have 2 HCl's. So now you have 2 hydrogens and 2 chlorines. Okay, so are we balanced now?
Yes.
Yes, we now have the same numbers of atoms and the same numbers of each type of atom on both sides. So my equation is now balanced. Okay. So now we have satisfied the law of conservation of mass. We have a real chemical equation here. Okay, let's try another one. Okay, so here we have aluminum, solid aluminum metal mixing with oxygen gas. And out of that, we are getting Al2O3. Right, remember aluminum is a +3, oxygen is a -2. So when these two things pair up together, we get Al2O3. So take a second, count the number of atoms and list them under the equation and compare each side, okay, and see what you come up with. So take a second. I want you to count the aluminums, count the oxygens on both sides and see what you get. Okay. So hopefully on the left, you got 1 aluminum and 2 oxygen, right? We don't have any coefficients. There's no coefficients out here. There's a little imaginary 1 down here next to the aluminum, and there's a 2 next to the oxygen. So that means we have 1 aluminum and 2 oxygen. Okay, on the right-hand side, we have 2 aluminums and 3 oxygen. Again, this comes from these little subscripts down here. This little 2 here tells me I have 2 aluminum, and the 3 here tells me I have 3 oxygen, and there is no coefficient here. So we have 1 aluminum on the left, 2 aluminum on the right, 2 oxygen on the left, 3 oxygen on the right. So what do we need to do, right? We need to balance this, and it's clearly not balanced. So we need to start adding coefficients. We need to start adding coefficients to see if we can balance this. Okay. Do you guys want to try and see if you can figure out which coefficients will make this balanced? I'll give you a minute to try, and then we'll talk about it. Okay, let's take a look. So one of the first things we usually try is looking at that aluminum. We can see we have 1 on the left, 2 on the right. Let's try adding a 2 in front of the aluminum to balance the aluminum atoms. So now that gives me 2 aluminum. I still have 2 oxygen, 2 aluminum here, 3 oxygen here. So the only thing we changed by putting that coefficient in is just the aluminum. So now my aluminums are balanced, right? I have 2 aluminums on the left, 2 aluminums on the right. But my oxygens are still not balanced. So anybody figure it out? What could we do to fix the oxygens? I have an even number and an odd number there. Hey, anybody got any idea?
So we need to put a coefficient of 3 on the oxygen gas in the
Yep.
reactants, and then put a coefficient of 2 on the molecule on the product side.
Yep. So that would fix it, right? If you put a 3 here, that would change this to 6 oxygens, and a 2 here would change that to 6 oxygens, right? So that would definitely help. But doing that, putting this 2 here, this 3 here only affects the oxygens, right? But this 2 here, what else does that change?
The aluminum.
Yeah, it changes the aluminum, right? So if you adjust the numbers, right, we now have 6 oxygens here, but in doing so, we have messed up the aluminum, right? So now my oxygens are balanced, but my aluminums are not. Anybody know what can we do to fix this?
Just put a coefficient of 4 in front of the aluminum.
Yep, if you change that and put a coefficient of 4 instead of a coefficient of 2 in front of the aluminum, your equation is now balanced. So you need 4 aluminums, 3 oxygen gases in order to make 2 aluminum oxides. Okay. So sometimes you might have to change a number more than once. Okay, sometimes you might have to change a number more than once in order to get a correctly balanced equation. Okay. All right. So now that we know how to balance an equation, let's look at what are the different types of equations. Okay. So I know this is a really long list of types of chemical reactions, but I promise it's not as bad as it sounds. So some of the basic types are something called synthesis, decomposition, combustion, single replacement, double replacement, oxidation reduction, acid-base reactions, and precipitation reactions. Now notice these 3 down here that have stars. That's because these are subcategories. So if you're an oxidation reduction reaction, you are also one of these, right? So you might be a single replacement and an oxidation reduction, or a double replacement and an oxidation reduction. An acid-base reaction, right, is also a double replacement reaction. So these are subcategories. So your main categories are synthesis, which is also known as combination, right, depending on what book you're looking in. Synthesis, also known as combination, decomposition, combustion, single replacement, and double replacement. Those are your main categories. Your subcategories are oxidation reduction, acid base, and precipitation reactions. Okay, so a synthesis reaction is when 2 or more substances combine to make a new compound, also known as the combination reaction, because you're combining 2 things. Okay, so synthesis, which is also known as a combination reaction, is when you have 2 or more things that come together to make a new compound. So this is what the general equation looks like, right? Substance A plus substance B join together to form a new substance, where A and B could be an element, molecule, or compound. So you have 2 things coming together to form one thing. So one thing, on the other side of the arrow, they have combined to make one thing. So in a combination reaction, right, you will have two or more reactants, only one product. Okay. The way to identify easily a synthesis or combination reaction is you will have multiple reactants, two or more reactants, only one product. If you have more than one product, you don't have a combination reaction. So remember, a synthesis or combination reaction is two or more things coming together to make one thing. So in order to have a combination reaction or synthesis reaction, you can only have one product. Okay. So an example of a synthesis is sulfur dioxide plus water gives you sulfuric acid. Sulfurous acid, sorry, not sulfuric, sulfurous. Okay. Sulfur dioxide plus water gives you sulfurous acid. Okay, so two things coming together to make one product. So reactant A plus reactant B gives you a single product. Okay, so you need to be able to identify what a combination or synthesis reaction looks like. And you can identify it by remembering that in order to have a synthesis reaction, multiple reactants, one product. Okay. A decomposition is the opposite. It's the backwards, right? It's one thing breaking down into two things. So it's decomposing, right? Remember, decompose means to break down. So a decomposition reaction is when one compound breaks down into two or more substances. So now you have one reactant, multiple products. Okay? One reactant, multiple products. So a decomposition reaction is when one thing breaks down into multiple things. The general equation always looks like this: one product breaking down into its parts. Okay. So again, X and Y represent an element, molecule, or compound. Okay. And an example of this is sodium nitrate breaking down into sodium nitrite and oxygen gas. Okay, so one thing is breaking down into two or more things. So sodium nitrate breaking down into sodium nitrite and oxygen gas. Okay, that's a decomposition reaction. Okay. A combustion reaction is when a substance combines with oxygen and in the process gives off energy in the form of light and heat. So what they really mean is basically an explosion, right? A combustion is when stuff burns up in oxygen. Okay. And the general format of this thing looks like this, right? You have some substance that combines with oxygen gas, right? And it gives off energy in the form of light and heat. What it really looks like in terms for us, general chemistry, a combustion reaction is usually a carbon containing compound, right? So some sort of carbon containing compound pairing with oxygen gas. And when that's true, when you have this carbon containing compound, your products will always be carbon dioxide and water. Okay. So an easy way to recognize a combustion reaction is that one of your reactants will be oxygen gas, right? And generally for the purposes of Gen Chem, your combustion is going to be some sort of carbon compound, right? So some sort of carbon compound plus oxygen gas, and your products are carbon dioxide and water. So when you're identifying a combustion reaction, right, look for a carbon containing compound and oxygen gas as your reactants, and carbon dioxide and water as your products. And heat. They don't show it, but one of your products is heat, right? You're burning this up, you're producing heat. Okay. single replacement reactions are just like what they sound like. So one element comes along and replaces another element in a compound. Okay, so a homewrecker comes along and steals your mate, right? One element replaces another element in a compound. So the general equation, right, is that C comes along, kicks D out, and takes its place. Okay, where C, D, and F are elements, and CD and CF are compounds. Right, so C comes along, kicks D out of its spot, and steals it. Right. So this is a single replacement reaction. One element replaces another element in a compound. Okay, an example of this looks like this, where iron comes along and kicks out the hydrogen and steals the oxygen. So now iron and oxygen are paired together and hydrogen is left by itself. So to identify a single replacement reaction, okay, 2 reactants, 2 products. But on both sides, one of the reactants is not going to be a molecule. It's going to be by itself. And on the other side, same thing, right? You have things by themselves. Iron started out by itself. It stole oxygen, now leaving hydrogen off by itself. Okay, so a single replacement reaction, again, is where one element comes along and kicks another one off, taking its place. Okay, so single replacement reaction. Double replacement reaction is just like it sounds. Instead of one thing coming along and kicking out the other thing, we now have 2 things swapping spots. Okay, so 2 things, right? 2 elements switch spots in their molecules. These are ionic compounds, right? So 2 ionic compounds exchange ions in solution to form 2 new compounds. Okay. So again, we have 2 things swapping spots, right? G was partnered with H and J was partnered with K. At the end, G and K are now partners and H and J are now partners. Okay, so again, we have 2 things swapping spots, right? G was partnered with H, but they decided they didn't want to be partnered with H anymore. So G and K came together and H and J came together. Now, can somebody tell me why I see that G, right, pairs with K. Why don't G and J pair together? Why don't we make a compound where G and J come together?
Because they have the same charge, like positive charge.
Yeah, they're both positive. So they're both now electron deficient, right? Positive charge thing and positive charge thing. When they get too close to each other, they're going to repel, right? They're not going to have any force of attraction. There are no intermolecular forces that will bring those things together because you have 2 positively charged things. So they don't want to pair up. G and J have no interest in each other. Right? And neither do H and K, right? H and K don't want to pair up because they're both electron rich. So H has a negative charge, K has a negative charge. H and K have no attraction to each other. There is no intermolecular force which will allow H and K to come together. So when these guys swap spots, the only partner available to G besides the current partner, besides H, is K, right? G and K can come together and H and J can come together. But G and J don't want to pair up and H and K don't want to pair up. So what does this look like in real life, right? This looks something like this. Iron was paired with sulfur, right? Iron is a transition metal. It likes to give away electrons and form a cation with a positive charge. Sulfur is a non-metal anion. It likes to make a -2. So in this case, we have a +2 iron and a -2 sulfur. Okay. Over here, we have chlorine, which likes to form a -1, right? In this case, the hydrogen is a +1. The iron is now going to pair with the chlorine. Positive cation, negative anion. So the iron and the chlorine pair up. That leaves the hydrogen and the sulfur to join forces. right? The hydrogen and the sulfur to join forces. Remember that sulfur likes to form a -2, right? And hydrogen, when given no choice, forms a positive. Okay, so again, we have swapped spots. The iron and the hydrogen are swapping spots. So a double replacement reaction is when two compounds switch spots. Okay. Oxidation reduction reactions. You'll also see this abbreviated as redox reactions because we're lazy and we don't like to say whole names of things. So formally, they're oxidation reduction reactions. Shorthand, we call them redox reaction. Okay. This is a subcategory which involves the exchange of electrons. All single replacement reactions are redox reactions. Okay, so anytime you see a single replacement reaction, it is automatically also a redox reaction. Okay. So the question is, can you tell by looking at this reaction if it's an oxidation reduction reaction? Let me ask you, is that a single replacement reaction?
No.
No, it's not. It's not. Remember, a single replacement is where one thing takes the place of something else. We don't have that going on here. What do we have going on here? What kind of a reaction is this one? Hold on. Boop. What do you think? There's your different types. What kind of a reaction is that?
Decomposition.
Yeah, it's a decomposition, right? We have one thing breaking down into two things. So let's see here. Okay, we have this KBr, potassium bromide, is breaking down into solid potassium and liquid bromine. So can you tell just by looking at this reaction if it's an oxidation reduction reaction? I'll tell you right now, the answer is no, right? You can't tell by looking at this reaction if it's an oxidation. The only one that you can tell immediately off the bat, instantly, if it's an oxidation reduction reaction is if it's a single replacement, okay? All single replacement reactions are redox reactions. If it's something else, you cannot tell immediately just by looking at it, okay? Instead, you're gonna have to understand the rules, right? And how to determine something called the oxidation state of the elements present. Okay, so again, this is a subcategory. It involves the exchange of electrons. The only one you can tell just by looking at it right away if it's a redox reaction is if it's a single replacement. Okay, all others, you're going to need more information. Okay. And I'm going to tell you about that more information later in the chapter. But for now, just know that the only way to identify just by looking at them is if it's a single replacement. All others, you need more information. Okay, acid-base reactions. That's another subcategory. This is when an acid and a base react together to form a salt and water. Okay. In order to identify whether you have an acid-base reaction, you have to know what an acid and a base are, right? So an acid and a base react together to form a salt and water. So here's an example of an acid-base reaction. Can somebody tell me what category did this come from? So this is a subcategory. What other type of reaction is this? And I'll pull them up, hold on. In here. Oh, further back. Here it is. This one here. Okay. Can anybody tell me what type of reaction is that? There's your choices. We have synthesis, decomposition, combustion, single replacement, or double replacement. And let's see here. Oops. There's my reaction again. What type of reaction is that?
Double
So let me
replacement.
excuse, is it a combination? Or do we have two things combining to form one thing?
No,
No, it's not a combination. Is it a decomposition? Do I have one thing breaking down into two things?
No.
No. Is it a combustion? Do I have a carbon containing compound pairing up with oxygen, producing carbon dioxide and water?
no,
No. Okay. Is it a single replacement? One thing taking the spot of something else?
it looks like a double.
Yeah, it's a double, right? It's not a single replacement, because if it was a single replacement, one of these things would have to be by itself. Okay? Yes, it's a double replacement. The sodium, right, and the hydrogen are swapping spots. So an acid-base reaction is also always a double, right? A double replacement reaction. So acid-base is a subcategory. It's a subcategory of a double replacement. Okay. And it's a specific one. And you always, when you react together an acid and a base, you always get a salt and water as your products. But I guess we should identify what a salt is, right? It's not what you go to jail for when you get in a bar fight, right? We're not talking that kind of assault. We're talking salt in the chemistry terms. Okay. So a salt is an ionic compound, basically. And it's any ionic compound whose cation is not hydrogen, because hydrogen is not a metal. So remember, when we're talking ionic compounds, we're talking a metal paired with a non-metal. Hydrogen is not a metal. So when we're talking about a salt, we're talking about cations, right? Your metal cations. So lithium, sodium, potassium, beryllium, magnesium, titanium, gold, silver, right? A metal cation and a non-metal anion that is not hydroxide. Okay, that is not hydroxide. So any of those other anions, right, including the polyatomics, right, including sulfate, sulfite, nitrate, nitrite, carbonate, bromate, right, any anion, including the polyatomics, but not hydroxide. And there's a reason for that. And that's because when you're identifying a base, most of the bases you're going to deal with this semester in Chem 1 have hydroxide. So sodium hydroxide in this case is a base. So when you see that hydroxide ion, a little bell should go off. Ding, 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 ding. Oh, that's a base. Okay. To identify the acid, remember when we were talking about nomenclature, we said that to identify the acid, you were looking for one thing. Anybody remember what that was? What did we look for to identify an acid?
It has hydrogen.
It has hydrogens in it. Yep. So remember we talked about that, guys, when we were doing nomenclature, when we were talking about polyatomic acids, sulfuric acid, sulfurous acid, phosphoric acid, hydrochloric acid, hydrobromic acid, right? In every one of those instances, they started out with hydrogen. So what you're looking for is a hydrogen and a hydroxide. And that's where your water comes from, right? Remember, water is H2O. So in this general equation, you always get water as a product. Well, it comes from the H on the hydrogen, right? The H on the acid pairing with the OH on the base. H and OH pair together to make water, leaving the cation and anion of the base and the acid to pair up. Okay, so acid-base reactions, you can identify them by looking for a compound that starts with hydrogen and another compound that ends with a hydroxide. And if one of the products is water, you can be pretty sure that in addition to having a double replacement reaction, you also have an acid base. And this is called an acid-base neutralization reaction. Okay. An acid-base neutralization reaction. Okay. And again, you can identify that by looking at your compounds. If you have a compound that starts with hydrogen, right, and it's paired with something that has hydroxide in it, and one of the products is water, you go, oh, okay, I know, I have an acid-base reaction. Okay. So this is where we're going to stop for today. We're going to stop here. Okay. We still have many, many more lectures in this chapter to go, so don't panic just yet. Okay, so what did we cover today? Today, we talked about how to read a chemical reaction and describe it, including states of matter, right? Solid, liquid, gas, aqueous. We talked about how to balance a chemical reaction. And then we just started with our classifying of chemical reactions. So we still have some more work to do on classifying our chemical reactions. And then we're going to go into writing a balanced. So on Wednesday, or by Wednesday, you guys will have a course ticket due. You also have a lab, right? You also have a lab due on Thursday. I strongly recommend you guys put together a contingency and contact your lab professor and ask him to push the due date back on that back a little, unless you guys want to see if you can get through it. But we didn't cover, we talked about acid-base reactions today, but we did not get to talking about the stoichiometry. Okay, so you may want to, and if you tell him, you can tell him to ask me, I will back you guys up. We didn't cover that yet, okay? So course ticket on Wednesday, you do have a lab due Thursday. Again, I definitely recommend you talk to your lab professor, see if you can get that pushed back. You will also have a homework assignment due on Sunday, right? Based on some of the stuff we're talking about today, plus the stuff we're going to talk about on Wednesday. Anybody have any questions for me? If you sent me an email about your exam, I did go through and look at those and responded to you. I also fixed the quizzes. You can see for 7 and 8 now what you got wrong. I did that this morning. So if you went in yesterday, you probably didn't see it yet, but I did this morning. I went in and fixed those quizzes. Any questions for me?
Yeah, I have a question from my exam. It was
Sure, what's up?
question 12
Mm-hmm.
on my exam. It was about hydrogen bonding. And I just don't
Okay.
know how. I got partial credit for it, but I just feel like I got all of it. I just don't see how I
Okay.
didn't. So if you
Hold
could just
on,
look
let
at
me
that,
pull
please.
Cengage up real quick. Do you remember what question it was, Will?
It was question 12.
12, okay. Give me a second here to sign in. Okay, let's see here. Question 12. Okay. Let's see here, exam 3. Will, where are you at? There you are. Okay. I'm almost there. Sorry, I had to go through about 14 pages to get there. All
No,
right,
you're fine.
hydrogen
You're fine.
bonding. Let's see here. So it looks like you got. Okay. Which of the following would be expected to form hydrogen bonds with water? So you got that one right. That one right. That one right. Ah, I see. You didn't select the propyl formate.
Okay, which one was that? Does it say which letter?
Yeah, it doesn't have letters on mine. It just has the molecules. But hold on, I'm looking at it right now. The propane is not correct.
Because I know one of them had.
I would not. So the Cengage is incorrect. It's asking you to understand rules based on organic chemistry. I would not, there's no hydrogen on those 2 oxygens. So
Right.
I'll give you credit for that, Will, because that's a little bit more advanced. That particular example is a little bit more advanced than what we did. So
Okay.
yeah, I'll give you credit for that.
Okay, thank you.
The others, yes, you were correct. You had everything right except that one, and that one is not.
Yeah, because that one didn't have an oxygen bonded to a hydrogen. And
Yeah, it has oxygens in there. So what they're asking you is the water, because it's asking you if it will form hydrogen bonds with water. And water does have a hydrogen bonded to an oxygen. So that hydrogen would be attracted to the oxygens on that other molecule. So even though that molecule doesn't have a hydrogen bonded to the oxygens, it has oxygens available for the water to be attracted to. But I didn't cover that in class, so I'll give you credit for that.
Okay, thank you.
You're welcome. You got a question for me, Ian? I know you don't have a microphone.
Actually, I do have one more question.
Sure, what's up?
The extra credit.
Mhm.
Have
I
you-
know, I'm so sorry. I still haven't stuck it in there.
Okay,
I
no,
promise I will not forget you guys.
like yeah, I don't really care when you put it in. I just want to make sure it was on there. You know, like I got it.
It
But it's
will,
a-
it
it's
will. And we have another one coming up. I'm gotta look and see what the date is. I'm not running it, but somebody else is running another review session. And there will be at least one more after that. So there will definitely be a couple more opportunities as well.
okay. I was just making
And
sure you
I
haven't
promise I have
put it
not
in.
forgotten. It's one of those things where I have to go find all the emails you guys sent me and add it all up. That's why I haven't done it yet.
Yeah. Okay.
But I
No,
swear I'll do it.
that's fine. I was just making sure. Yeah.
You have an A anyway. I mean, you can't get any higher than an A. So
True.
I
True.
won't panic too much. You have an A. Okay, Ian, were you waiting for me? Did you have a question, Ian? Or did you walk away from your computer and just leave it on? Ian. No? All right, I'll be around all day if you do have a question.